Good day to you. Welcome to lectures on digital control systems. And in our previous lecture, we have discussed complete state controllability, and in continuation to that, we will also discuss complete output controllability. And since I have already discussed complete state controllability in our previous class, I would just like to review what is a complete state controllability, and then we will proceed to complete output controllability. And here, the equation that we have considered here is the state equation, which is g into x of kt plus h into u of kt, and y of kt is equal to c into x of kt is what we have considered in our previous class. And that is with respect to complete output controllability. We will discuss output equation, and for the state controllability we doesn't require this output equation because we are only considered with the state vector, right? And we know that we have n state vectors, state variables, and m inputs. Therefore this is also an n by 1 vector. Therefore this is an n by n vector, and this is an n by m vector. Okay, so and this x of kt is the state vector at kth sampling instant. U of kt is the state input vector at kth sampling instant. X of k plus 1t is the state vector at k plus 1th sampling instant, right? And controllability or state controllability, right? And what is complete state controllability? By definition, we can say that if it is possible in any linear time invariant discrete time control system of this sort, the definition of controllability states that any linear time invariant discrete time control system of this sort is completely state controllable when it is possible to transfer the system state x of kt from any initial desired state, any arbitrary initial desired state, to any arbitrary desired final state. I will say T0 is the initial time and Tf is the final time, and these are with respect to kt, depends on kt, or k is the number of instants, right? Where with a finite time period or sampling periods, or let us say the sampling periods is this one, sampling periods is this one, n sampling periods or k sampling periods. I can say this as nt, right? So x of t0 is 0t, x of tf is nt, right? From 0 to n within n sampling periods, if it is possible for us to transfer the system state x of kt from x of t0 to x of tf, where t0 and tf are initial time and final time, right? And how is this possible? With the help of the unconstrained input vector, u of kt, with the help of unconstrained input vector u of kt, or unbounded input vector, right, u of kt. So this is controllability. Complete state controllability is defined by if any linear time invariant discrete time control systems x of k plus 1t is equal to g into x of kt plus h into u of kt, right? If it is possible to transfer the system state vector x of t from any arbitrary initial state to any arbitrary desired state within a finite time period and sampling periods by the help of an unconstrained input vector u of kt or an unbounded input vector u of kt, then the system is said to be completely state controllable. Right. So this is definition of complete state controllability. Definition of control state controllability. Right. Now let us see in our today's lecture what is complete output controllability. Now for output controllability, I will consider this same equation, y of kt is equal to c into x of kt. Right. To determine complete output controllability, what is the necessary and sufficient condition here? X of k plus 1t g x of kt plus h u of kt, and y of kt is equal to c into x of kt, right? So with this equation, we know that the solution of this state equation is x of kt, right? So what is this equation? Or let me say n sampling periods, therefore nt, if I substitute here, g power n x of 0 plus sigma j is 0 to n minus 1 g power n minus j minus 1 j h u of jt. Right, this is the solution of that transfer function. Now x of nt. Now if I want to find out y of nt here, y of nt, what is happening? If I multiply c into x of nt, y of nt is c into x of nt, x of nt is this, so I will multiply this equation with this. So I have c g power n x of 0 plus c sigma j is 0 to n minus 1 g power n minus j minus 1 h u j t. Right. So if I just y of nt minus c g power n x of 0, right, if I elaborate this, I have taken this term to the left hand side and I got this. Now with this, what is this? What is the equation? If you expand this term from j is equal to 0, what is happening to us? What is happening to this equation? J is equal to 0, g power c into g power n minus 1 h u of 0, right, plus c into g power n minus 2 h u of t when j is equal to 1. So on, I get plus c into g power n minus 1, j is n minus 1 and n minus 1, both getting cancelled, g power 0 h u of n minus 1t. Right, so this is our equation. Now this is our desired state. You can consider this from final output to the initial output. Right, final output to the initial output, and you are getting this. If you write this in matrix form, how do we write this? U of n minus 1t. If I consider here u of n minus 1t, u of n minus 2t, so on, u of t and u of 0. If I consider this equation here, matrix form, then what is the equation that I get here? U of n minus 1t is ch. It is a matrix, so I will separate it with a straight line, dotted line, and cgh. Right, the previous case, cg power 1h is what will be left over for us, and so on. Cg power n minus 2, cg power n minus 1. Right, so I will get this into h, into h. Right, so this is what we are going to get: ch u of n minus 1t, cgh u of n minus 2t, cg power n minus 2h u of t, and cg power n minus 1h u of 0. Now this is our equation. Okay, and with this equation we can find out that if this is the controllability matrix. Controllability matrix for output controllability. We are discussing output controllability here. Therefore, we can say that this is a matrix for output controllability. And when this is considered, what is happening? You are still having n values, right? So the rank of this matrix, rank of this controllability matrix QC, you can say call this as QC, right? It should be equal to n because it is an n vector, 1, 2, so on n. So you can say that it is an n vector, or 0 to n minus 1. It means that you have n rows, therefore you can have that rank of QC is equal to n. If rank of QC is equal to n, then the system is said to be completely output controllability as far as these equations are concerned. Therefore, by definition, you can just put your definition in the other form. If for any linear time invariant discrete time control systems of this sort, and when you have y of kt is equal to c into x of kt, then if the rank of controllability matrix ch, cgh, so on, cg power n minus 2h, cg power n minus 1h is equal to n, then this system is said to be completely output controllable. System S, let us say S is called the system, and system S is completely output controllable. That is what we have discussed so far in this equation, right? And there is one more equation for us with plus du of kt. Now what will happen if you are having this output is also depending upon the input. Initially there is no input vector that is related to the output, but here now when you are having this input vector also related to the output, then you have this equation with this solution being the same, and y of nt is equal to c into g power n x of 0 plus c plus du of nt plus du of nt. Now if you can represent this equation again, if I take this to the other side, what will happen to this? You are having this and plus du of nt. Now it has become an n by n plus 1 term. You can say 0, 1t, n minus 1t and nt. So it is n plus 1 term, and therefore I can write this as d, same thing here, dch, but dunt. So I can put it as unt. So this is the only difference that we have here, and dch, cgh, cg power n minus 2h, cg power n minus 1h. So the same equation is holding good, and the controllable, this is called the controllability matrix, and the rank of this matrix must be equal to n again. So by definition of output controllability, you can say that if in any linear time invariant discrete time control systems S, where S is represented as x of k plus 1t gxt plus h u kt, y of kt is equal to c x of kt plus du of kt, and the solution is given like this, and such equation, if it is subjected to some controllability test, the controllability matrix dch, cgh, cg power n minus 2h and cg power n minus 1h, it must be of rank n. If it is less than n, that is, if the determinant of this matrix is equal to 0, then it is the rank of the matrix is less than n. That is, the matrix must not be singular matrix, it should be non-singular in nature. Only then you will have this rank of QC is equal to n. If this rank of controllability matrix is equal to n, then the system is said to be completely output controllable. Completely output controllable. RPM.